Good evening. Good evening, ladies and gentlemen. It's my pleasure to welcome you all here this evening. The distinguished guests, the alumni, and our principal guest this evening, Dr. Stephen Chu and his wife, Jean Chu. We're delighted to have you here. My name is Richard Simmons. I'm a board member of the Berkeley Club of London and chair of this evening's event. We're delighted to see you all here to join the discussion with our Nobel laureate, Dr. Stephen Chu, director of the Lawrence Berkeley National Laboratory and Berkeley Professor of Molecular and Cell Biology and of Physics. This evening marks the inauguration of the Berkeley Club of London. The goal of this evening is to share knowledge between our alumni, our distinguished guests, and Professor Chu, a scientific leader and key advisor to policymakers tackling the challenges of global warming. Dr. Chu will present an overview of the world's energy picture and will reference some of the groundbreaking research being undertaken at Berkeley. But before I introduce Dr. Chu, I would like to take a minute to acknowledge the very generous support of the sponsors of our event this evening, united by their interest in solving the challenges posed by energy supply and environment. Our thanks go to Accenture, AXA Insurance, Cisco Systems, and OpenLink Financial. I'd also like just to take a couple of minutes to tell you something about the Berkeley Club of London, which, as I've said, is formally launched this evening. The Berkeley community has enjoyed a long and successful existence in London. There are about 2,500 Berkeley alumni in the UK. And as the largest community of Berkeley alumni in Europe, Berkeley in Britain had been led by our dear friend and alumnus, the late Al Buck, whose wife Jill is with us this evening. Now, with the support of UC California House and the Office of International Relations at Berkeley, we're expanding the forum to connect alumni and friends of Berkeley with the exciting discoveries their faculty are engaged in that might have local relevance for London and the rest of Europe. And in the tradition of Berkeley, everyone is welcome to the Berkeley Club of London. But without further ado, permit me to introduce our special guest this evening, Dr. Stephen Chu. Following his presentation on solutions for global warming, we will open the floor for what I'm sure will be a lively discussion. But turning to Steve. Steve Chu was born in St. Louis and raised in New York. Dr. Chu earned an AB in mathematics and a BS in physics from the University of Rochester and a PhD in physics from UC Berkeley. His distinguished career in laboratory research began as a postdoctoral fellow in physics at Berkeley between 1976 and 1978. He then joined the technical staff at AT&T Bell Laboratories and later led Quantum Electronics Department, during which time he began his groundbreaking work in cooling and trapping atoms by using laser light, which later led to a Nobel Prize in Physics in 1997. In 1987, he joined the Stanford University faculty. Then in 2004, became director of Lawrence Berkeley National Laboratory, the oldest of the US Department of Energy's national laboratories, and one of 3 institutions forming the Energy Biosciences Initiative, recently funded by a $500 million grant from BP, of which Dr. Chu is the chief scientific advisor. Dr. Chu also co-chaired the Inter-Academy Council groundbreaking report released this month, titled Lighting the Way Toward a Sustainable Energy Future. The IAC represents over 150 scientific and engineering academies from around the world. Tonight, we are delighted to have Dr. Chu share his insights on the future for alternative and renewable energy with us. Dr. Stephen Chu.
So, thank you for that very generous introduction. And I made a little faux pas. I put my computer in hibernate. But while it wakes up, and hopefully it wakes up sooner rather than later, I have to say that that sounded very impressive. Who was that person you were talking about? While I stole for time, oh, this is interesting. Okay. You want to read some unread messages? Let me just see. Okay, I think I'm ready. But I have to tell you a funny story. I come from a family of overachievers. They're terrible overachievers. I have two brothers, one older, one younger. Between the two of them, they have, I think, 6 advanced degrees beyond BA. I only have 1. And, like an MD, a PhD in physics, a PhD in biochemistry is one brother. That was the dumb one. He's a professor at Stanford. The smart one got a PhD at 21, got a law degree, got a whatever goes beyond the law degree, and is now one of the chief intellectual property rights lawyers, litigators in the United States. He's the smart one. I'm somewhere in the middle. And when I heard I got a Nobel Prize, I called up my mother. We waited for a few hours and called her up at 7 a.m. and said, Mom, I just wanted to know, I got a Nobel Prize in physics. And she said, that's nice, dear, but when are you going to come to visit me next? So anyway, so this is my family. So I want to talk about energy at Berkeley and Lawrence Berkeley National Laboratory. Very briefly, unfortunately, I'm supposed to keep my remarks limited, so I just want to say briefly that the energy problem has many facets. There are environmental concerns. There's local pollution of generating energy, for example, coal. But there's also more global pollution in the form of greenhouse gases. It turns out that roughly 1/3 of the people in the world don't have access to any form of modern energy. 1.6 billion are off the grid. They don't have access to electricity, but a larger fraction burn twigs and dung and lumps of coal they find in very primitive circumstances. And so this is another issue. And then finally, in addition to all these other issues, as the world jockeys for access to fossil fuel, precious fossil fuels like oil and natural gas, there's clearly potential for geopolitical conflict as you try to guarantee access by either making friends or at least, well, whatever. But in any case, there's potential. So I would be glad to talk in the question and answer period about some of the evidence that convinces scientists, many scientists, that the globe is not only warming up, but it's mostly caused by humans. But in the limited time, I can't really talk about that. But I want to talk, and all of the predictions, some of the predictions, any prediction that has less than a 20% probability, most scientists don't really want to talk about. But once it goes to 50% or higher, then one is concerned. Now, the question is, how much can we trust these predictions? And for that, I first want to give you advice from the great American philosopher of the 20th century. His name was Yogi Berra. He played catcher for the New York Yankees. And he said many wise things, and in this particular instance, he said predictions are hard to make, especially about the future. Okay, so I'll give you just one prediction of the many things that we are beginning to see statistically. So, you know, if I were getting up here and saying that your recent storms in England were climate change, you would quite rightly say that's rubbish. And I would agree with that. A single event would never convince any scientist of any of that. But it's records of decades that suggest that these things are happening. The sea level is rising. But let me just talk about one, water shortages, which hasn't gotten very much press. There's also a fear of many other things, increased disease that are temperature-borne, water-borne, like malaria, cholera. But let me talk about one thing in water shortages, and it's provincial. It has to do with California. So this is a paper refereed by the National Academy of Sciences, 2004, one of the more prestigious journals in science, and it gives predictions. B1 is a prediction that the carbon equivalent will remain below 500 parts per million. We're about 420, 430 today. We started 275 before the Industrial Revolution. So we're a lot of the way there. Most people feel that we will exceed this limit. Okay? A1 is business as usual. In the most optimistic scenario, half to 3/4 of the alpine and subalpine forests that make up the California watershed will be gone in this century. Okay? And then Sierra snowpack will decrease 30 to 70%. In the more pessimistic scenarios, they're mostly gone. So this constitutes a substantial part of our water supply in California. So once the forests are gone in the mountains, water, when it rains or snows, tends to run off very rapidly. So you have flood situations. And so it's the trees that actually supply a lot of the gradual release of water, and of course the snowpack, because it melts, it takes until June to melt. British Columbia, there was a prediction, that 70–80% of the pine forests will be dead within a decade due to pine beetle infestation. The issue here is that during a frost, the pine beetle parasites are killed, and so their population is kept under control. But if it gets warm enough and they're not killed, they would ravage forests. So here's the prediction: 2013, 80% will be dead. This is a picture of dead pine forest still standing, and there's little lumps of green here. Is this the sky is falling? Well, not really. 40% is already gone. We're halfway there. And it was a little surprising that we got that way so fast. And it's also being predicted, and it's also true in the Rockies and in the Sierras. The pine beetles are going crazy because they're no longer being killed. So this is, again, a measurement. But it's also a prediction, but we're halfway there. We're getting there much faster than we thought. So this is one bit of evidence that we are concerned about. When these trees are gone, this is a watershed area. You sacrifice that. Okay? Let me try to talk about an issue which it's commonly thought that the more energy a country uses, the more prosperous it will be. And of course, the United States leads the pack. It's considered the most prosperous country in the world, and it uses the most energy. Now, it depends on how you measure prosperity, but in addition to the average GDP per person in a country, you also want to fold in healthcare, education levels, and everything else. So there's other measures like the Human Development Index that tries to fold in all of these things. And I want to point out that this is Japan, this is Europe, this is Australia, United States, Canada. Norway is very energy rich, and so they don't really have to conserve. Kuwait, I don't know why Kuwait is that far down, but there are many Arab countries that are off the scale towards the wall. It's flat in terms of the prosperity of a country and their use of electricity beyond a certain level. And so we have to remember this, that the sort of level of prosperity in a country is not really directly linked to the use of energy. And in fact, one would like to bring all of these countries down to somewhere here or even further below. Why? So you can create headroom for developing countries so they too can share in some of the prosperity. Ultimately, you have to ask the question, why is it that, let's say, Americans or Canadians have more share of the world's resources than other people? Now, you can say, well, we got there first, we're returned, that's the way we want it to happen. But in the end, I think it becomes a morality issue. Where do you want the world to be? But this is not about sacrifice. This is not about doing without, because the essential question is not our use of energy, but our use of energy that has a carbon footprint or greenhouse gas footprint. So here's another plot. Now it's just GDP. It's not human index. And again, this is a time scale of the United States. As the United States went to a service economy, as it offshored a lot of heavy industry, and as its economy matured, our use of energy is roughly flat, mostly because heavy use of energy in industry has gone down. Australia is climbing up, trying to catch the United States, but the real question is, and here's Europe, France, because it's 79, 80% electricity generation by nuclear, has a much smaller carbon footprint. The United States really should be down here somewhere. In fact, the governor has stated as a goal by mid-century of this year to reduce the California carbon footprint by a factor of 5. There is a law that says we want to reduce it by 20% in 2020, by 2020. So the real question is, what are China, India, Brazil, and other countries, rapidly developing countries, are going to do? Are they going to follow in the footsteps of the United States, and all of a sudden they realize up here, oops, terrible mistake, we really wanted to be down here? It's going to cost the United States a lot because we have an embedded infrastructure that will make it harder for the United States to come down here than it would be for the UK, for example, to come down here. Or can we teach these countries how to grow in a sustainable way that embodies all the technologies we now know? And so this is going to be a crucial question. And to what extent can we offer world financial help in not charity, but financial means of helping China and India get there? So this is a crucial question. But if we don't do this, and if the United States does not come down, we are in big trouble. So energy efficiency and conservation is and will remain the lowest hanging fruit for the next several decades. There's no question about this. Let me give you a reason why, but fundamentally, going back to this issue, it's not going to be free markets alone that will force countries to take the proper path. The old joke is that after the Soviet Union collapsed, and you ask how many free market economists does it take to change the light bulb? And the answer is none. If the light bulb needed changing, free market economy would have done it. Free markets fail when there is what's called a commons problem. So what's a commons problem? It's a common shared resource. The fish in the ocean is a common shared resource. And so when one country or one sector doesn't have total control over this resource, they might think, well, I got to fish what I can fish because someone else might overfish and cheat me out of my fair share. Let me put it bluntly. That's typically what happens. That also happens in air and water pollution issues, sharing of water resources across borders, and the climate change issue and greenhouse gases is the ultimate commons problem. England, Great Britain can say, well, we're a small country, we really can't do anything about this, so what the heck, let's live life and enjoy it. Instead, I think perhaps a majority of the people in England might say, no, we might show a leadership position and shame the United States into doing something. Whatever the reason. It's also true in China. China is now seriously waking up to the issue that it's not purely economic growth, and this is all good news. Is it possible to conserve? California has done this. And actually, the University of California and Berkeley lab led the way in this one. In the mid-1970s, a professor of physics at University of California, Berkeley, and a member of the Berkeley lab left high-energy physics and devoted the rest of his career to helping solve the energy problem, and he decided the lowest hanging fruit was energy conservation. And many things that he started led to an absolute flattening of the electricity per person usage in California, while the rest of the country, minus the United States, was up here. It went up by 60%. Okay? Single-handedly, it really gave birth from the University of California, and something to be very proud of. There are many, many things that we can now do. For example, the Berkeley lab has helped design a new federal building. Buildings are 40% of the energy consumption in the United States. I was told today that buildings, residential and commercial buildings in England, are about 50%. You can, many, many progressive architects tell me you can save a factor of 2 in energy, which would have a payback in 5 years or less. This is one example. This is a federal building. Because it's a tower, you get a chimney effect. A chimney effect means you don't really need mechanical cooling for the ventilation. You can suck it up at the bottom and vent it at the top very naturally. You can build very large concrete structures that give you thermal inertia, and if you've ever gone to the castles in France, you find that in mid-August, when it's 90 degrees outside, the castles are cold because they're actually just heat conductivity in the ground, and they didn't really want them to be that cold, but with proper engineering, you can design any temperature you want and have a heat inertia that would then reflect more of the average temperature, nighttime and daytime, and extensive natural lighting, all of these things. With proper computer tools, we can actually predict within a few percent what the energy consumption of a building will be, just as we can predict within a few percent how an airplane's performance will be long before the airplane is actually built and test flown. And the simulators are very accurate. So we know this in buildings now. And so we can engineer the buildings for energy efficiency. And, so we have to do that. Now let me tell you a little bit about Lawrence Berkeley National Lab. So this is UC Berkeley campus. This is the famous football stadium. And this is the Campanile to orient you. And so Berkeley National Lab is on a 200-acre site overlooking Berkeley campus. It's a very distinguished laboratory. Berkeley has 15 Nobel laureates in science. Of those 15, 11 employees were employed at the lab. And many of them started their careers at the laboratory. 9 of them did their work at the lab. But now if you consider all the students and postdocs and young scientists who are trained at Lawrence Berkeley Lab, in addition to these 9, you can add another 40 plus. So this is an incredible legacy of training that came out of Berkeley Lab. Right now we have about 3% of the members of the National Academy of Sciences at the laboratory. Many of these are shared with the University of California, Berkeley. So there's a huge mention. There's 275 faculty members who are both on the faculty and also members of the laboratory. So without Berkeley campus, we would not be the laboratory we are today. And without the Berkeley lab, University of California Science would not be what it is today. When I came to the Berkeley campus and Berkeley lab over 3 years ago, I said, could I talk these sterling scientists who are mostly doing research in basic sciences to work on this energy problem? And so we quickly descended on how can we harness the energy of the sun to make new forms of energy. The most pressing immediate one is to get a substitute for petroleum. And there are many paths. You can grow plants to make cellulose. And then you have to convert the cellulose into biofuels in a much more efficient way. You can engineer microbes, algae or something to make fuels. You can, for example, take photovoltaics and really give a boost to its capability, make electricity, and once you have electricity, can you convert it into fuels? Or electricity itself would be a great thing. If you had electricity and could convert it to transportation fuel, then all sorts of other renewable energies can, or high capital intensive energies like nuclear energy at night would become very useful. Okay, so let's talk about biofuels. The first question you have to ask is okay, this is my little wifey telling me I have 5 more minutes. The first question about biofuels is, I've got a bet right in on this little talk that I can stop in 30. Is what happens over here in blue, it's too cold, not enough sunlight. In red, not enough water, it's desert. In black, you can grow food, okay? So the first thing you're struck with is there's a lot of desert in the world. So you look towards solar thermal photovoltaic. The trouble is you need about a factor of 3 before people start putting them on their rooftops without any subsidy, and probably more than a factor of 10 before you're willing to, power companies are willing to generate electricity this way. But the tantalizing thing is you need a few tenths of 1% of the world's desert at 20% efficiency, which we have today, to generate the current electricity needs of the world. So a few percent of the world's desert is all you really need. So it's only a matter about getting the cost down. We have a lot of solar power hitting the earth. And so we are working very hard to try to figure out how not to improve silicon technology, but go a radically new technology based on nanotechnology to create continuous reel-to-reel wet chemistry processes that allow you to stamp out these things at, you know, within a factor of 10 of the cost of white paint, quite frankly, is what you need. Sunlight to energy. We want to grow better plants, and we want to convert the plants into chemical energy. So here's a picture of a grass field in Illinois. In the fall, they cut the grass down to here, and in 1 year, it grew up to here without fertilizer, without irrigation. This is a very tall graduate student. She's 5'4". The amount of ethanol you can convert with the cellulose material is 10 times the amount of corn. And if you consider all these grasses plus the wood residues, the wheat straw, the rice straw, everything else, in the United States we have so much agricultural capacity. We're talking about using only half the surplus land in the United States to convert to satisfy half of all the U.S. gasoline consumption. These plants are great. No tillage for 10 years because they're perennials. They pop up again. They fix their own nitrogen, so that's why you don't need fertilizer for many years. And they withdraw very precious nutrients back in the soil, and there's lots less water pollution, lots less soil erosion. Everything's great except one thing. It costs about 2.5 times as much to break down the cellulose material into ethanol as it does to convert sugarcane or corn into ethanol. So this is a very clear goal. It's just exactly like the solar photovoltaic goal. And so we can set our sights in a very clear goal. Can we bring this price down? So how do we do it? Well, as mentioned, BP has partnered with UC Berkeley, Berkeley Lab, and Illinois to give us $500 million over 10 years. The Department of Energy has partnered with us to have $25 million a year for at least 5 years, probably 10, for a similar sort of venture. So with these kind of resources, we can take a totally fresh look at how do you convert cellulose into fuel and how do you make better plants. For example, this is a cartoon of a termite. It eats your home and converts cellulose, the wood in your home, into energy. But it actually can't, just like you and I, if we ate wood, we couldn't convert it into energy. So it has a deal with this is the stomach of a termite. There are many stomachs. In the stomach of a termite, there are microbial communities. Over 100 different microbes turn this wood into energy. They take a little carrying charge. They give the rest of the energy to the termite with instructions, go give me more wood. And so everybody's happy. The termite's happy, the microbes are happy, the homeowner is less happy. But So we are studying these microbes to figure out how they work. Can we make better microbes to turn this cellulose material into energy? One of our scientists, Jay Kiesling, he's one of the poster childs of a new field called synthetic biology, where you put in all sorts of genes into a microbe to really transform this microbe into a little chemical factory. And what he did is he transformed this microbe into making an anti-malarial drug, Artemisin. That's Jay Kiesling. He's a very clean-looking guy. And this has got a notice of the Gates Foundation, and there's $42 million grant to convert this from a microbe. I think I got 3 more minutes. Less. There's a bottle of wine right in this. Into a commercial company, and they're ahead of schedule to deliver in 2008, 20 cents a cure for malaria. This same technology can be used for biofuels. Ultimately, what do we really want to do? Man first learned to fly by imitating nature. This is Leonardo da Vinci looking at birds. This is the first picture of a bird. But this is an airplane was a hybrid. The wings look like birds, sort of, but the engine that drove the airplane looked nothing like a bird. It was a gasoline engine. So, can we develop an artificial photosynthetic system that takes water, turns it into oxygen, hydrogen, takes carbon dioxide, turns it into carbon monoxide? Those are the constituents you need to assemble a hydrocarbon. Why is this important? Because water, in the end, will be the limitation. So, if we're going to supply transportation fuels for all the airplanes and trains of the future, we need to eventually get this. And this is a project we started at Berkeley. So let me close by saying this is a very famous picture taken when the first Apollo mission that rounded the backside of the moon came back and saw Earthrise. Let me remind you, this is not a good place to live. This is a very good place to live. This is the only place within striking distance we can live. Now, if the climate changes drastically, will life be wiped out? Absolutely not. But a lot of humans, a lot of plants and animals will face extinction. So let's think about trying to preserve what we have. Thank you. 29 minutes.
Who would like to get us underway? Gentleman in the front.
I can probably shout, if that's okay.
Yes, I think.
We have the same problem in the room. We have humidifiers and dehumidifiers. What do you think about the possibility of having a carbon dioxide dating?
Very good question. So the question is, we've got a lot of carbon dioxide in the air, and let me actually amplify your background of your question. We will probably exceed 500 parts per million of carbon equivalent. I'm afraid we might exceed 600. There's a lot of us very nervous if we go beyond those levels, what will happen? You know, there's reasonable probabilities that, you know, some very serious things will happen. So can you suck the carbon dioxide out of the atmosphere and fix it in some way? Plants do this. There's a very slow sequestration of plants, but we can possibly look at those grasses that I just showed you actually fix a lot of carbon, put it in the soil. Now, it could be very temporary. If you till the soil, you release it back up. But trees actually fix more carbon. The ocean fixes carbon at a very, very slow rate, and so does the land. But we already know from doing genetic sequencing of a very fast-growing tree, a so-called poplar tree. We can alter the genes so it fixes more carbon. If we use those perennial grasses to grow biofuels, not corn, corn is a disaster. But if we grow some grasses and we don't till the soil, can we suck some of that? That buys us time. It's not going to be forever. I'm not going to stand there, you know, it can buy us 30 years, it can buy us 50 years, it can buy us some time. We can possibly suck some of it out if we take those plants and convert it into a fuel where we eventually convert it to hydrogen or something like that, and then take all the carbon, put it on the ground in sequestration type of thing, that's economically not close to being feasible. Then it becomes a big negative drain in carbon. So we can take plants, we can turn it into, we can burn it in a very high technology way, take the carbon out of the stack, put the carbon back in the ground, and generate energy. It's not commercially feasible right now. So are there better ways? Well, there might be, but we don't know yet. And now there's geoengineering ways that people are toying with, but we know very little about that. You've heard of sprinkling the ocean with iron to make algae that fixes carbon. We don't know enough about the ocean to trust that idea at the moment, but we can look at it. Someone suggested that those little critters, if any of you have snorkeled, and they feel like sand hitting your snorkel mask, they're little critters with little carbonaceous shells. They actually fix carbon in the form of calcium carbonate. They die, they sink to the bottom, and that is actually mineralized because it's covered up. There's good news and bad news. We can maybe make them grow bigger shells. That's the good news, but it's messing around with Mother Nature at a level that we have to be very cautious about. The bad news is because of the increased carbon dioxide, the ocean is getting more acidic, and we know as the pH changes dramatically, those guys will not form shells. This we know from laboratory experiments. Those guys don't form shells, the whole food chain of the ocean breaks down. That would be not so good. Okay, that's a low probability event in this century. So let me not alarm you, but here.
Could I ask you to kind of give your name and before you give your question?
My name is Tom Ludwig, Berkeley.
From Berkeley.
Are you aware the city of Berkeley is sponsoring the installation of solar panels on all houses and commercial buildings in Berkeley?
Very much so.
Oh.
In fact, I've volunteered, I've gotten to be friends with the mayor of Berkeley, and there's a little group of us that actually tries to help Berkeley figure out, they want to reduce their carbon, they want to be a leader, not only in California, which is a leader in the United States. There's all sorts of things that one can do. Now, I have to say, it's a bunch of, pretty busy people who are willing to help Berkeley do this. And it's kind of amusing because the first impulse is exactly what you said. Put on solar cells on roofs. But this panel of experts are saying, that's all great, it makes you feel good, but the most important thing you can do is stop the thermal leaks, insulate your house. Stop the leaky windows. The hardest thing to do is to just encourage public transportation rather than personal vehicles. Okay? The solar photovoltaics actually come pretty down the list of what would make the most impact on the carbon footprint. One person said in this meeting, people don't really want to turn off their standbys and electrical appliances or buy better ones. So what they do is they say, if I stick up solar panels, I'll feel good, and it's also a good sign to the rest of my neighbors. But it's not the best thing they can do with that money.
Jeremy.
Richard, thank you. Jeremy Swan from Cisco Consulting. Dr. Chu, I just wanted to get your feeling about how optimistic or pessimistic you are about the Realpolitik within the global framework. For example, do you really believe that the American government or the British government or the Chinese government is really going to put resources, time, money behind this when certainly the Western democracies electorate simply pay lip service to a lot of the issues but won't do anything about it? We happily, most of us in this room, certainly myself and probably most people, are living in a golden age. Mm-hmm. And we do our things, and we play golf, and we go home, and we have our pension plans and all the rest of it. And do we actually really have enough ability and care to make the change that we have to make? And if we don't, some of us do, I'm sure, and some of us don't, will politicians who are based on 4 or 5 year terms, where their interests are not the chattering classes as some of us, probably myself, are in, but the people who really vote care about, when they care about their trucks and their houses and their farms, etc., and not about big issues like this. And I wondered what your view about your optimism and pessimism that we can really make change at the political level is.
Yeah, that's cuts to the heart of the matter, actually, that question. I think there's a very rapidly changing scenario. I think Europe and California might have led the way. The United States is lagging. Very recently, only in the last half year, do I see really sincere efforts in China beyond just pure economic development. But in the end, your question is, well, I've got my life and I don't want to change my ways and habits, and what sacrifice am I going to be asked to make? I think it's fair to say in the United States currently, if they were asked to pay 20% more for renewable energy, because it costs more, many people will say no. Okay, so this is an education process. If you start to say what is, and it's risk management, but it's risk management for your children and your children's children. But you don't have to go, we're not talking 1,000 years ahead, we're talking 50 years. You saw the predictions in California. Now, how good are those predictions? You know, remind you of Yogi Berra, but it's greater than 50%. So if it's greater than 50%, that the watershed system in California is at great risk. We're not talking about the ski industry. We're talking about drinking water. The ski industry will be gone. So we're talking about drinking water. Then how do you get people geared towards looking 50 years ahead and saying this would be catastrophic? The other thing is the switch is not going to be fast. There's huge inertia. Energy in the United States is a $1 trillion plus industry, and there's a lot of stakeholders, and a lot of those stakeholders don't want to change. And they don't know any other way, and so there's always going to be inertia. I think it's ultimately going to be education for the policymakers and eventually for the public to say, you really want to leave this to your children. It's not even your grandchildren. Well, some of you will be your grandchildren, but, but the younger you, it would be your children. And so that's the issue. It ultimately becomes a morality issue. And that's all I can say.
The lady, you want to ask a question? Lady, well, yes. Yeah. Would you?
Isabel Hilton, I run China Dialogue, which talks about these things in China. Excuse me. I'm interested in, I mean, you said, for instance, that ocean acidification was not going to be this century. I've been looking at the disparity between the scenarios in the IPCC report and those places where one can measure the speed of change, like Greenland and Ilulissat and all those
You
places.
notice they don't match.
They don't match at all.
Yes, IPCC is much more conservative.
Much more conservative.
That's right.
And certainly in Greenland, things are happening now that were predicted 25, 30 years hence. So when you say it won't happen this century, or I wonder if is that statement taking into account feedback loops and what, the trigger points for feedback, which seem to me, if you really think we're going to 500 or 600 parts per million, you're talking 2-3 degrees, and that's very serious.
At 500, 600, there's a big enough air bars it could be 6 degrees centigrade.
Well, absolutely.
Right.
But and hotter in some places like the Himalayas.
That's world average. The northern hemisphere much hotter.
And all of Asia's water supply, for instance. So, I mean, I really appreciate your relaxed style. I just wonder whether that's really how you feel.
I'm trying. No. Let me explain where these IPCC predictions, as I know them, come from, because I know a lot of the people on those study panels. You talked about tipping points. So these are points where, above a certain temperature, all of a sudden there's massive amounts of carbon in the frozen tundra and methane in the frozen tundra that could be released. There's geological evidence that happened in the past, the distant past, 15 million years ago. Sudden huge release of greenhouse gases, sudden spike in temperature. Then all of a sudden what humans put in greenhouse gases becomes very small to the millennia, hundreds of millions of years of sequestration that got carbon out of the atmosphere and put it in the frozen tundra. Okay? When that goes, we don't really know what's going to happen. The probability that goes, we don't really know at what temperature. It was not in the IPCC report at all. Why? Because the issue there was, well, we don't know when it's going to happen, so we shouldn't put it in. There was huge political pressure not to put in things that we were uncertain about. We didn't know what temperature. So we, the IPCC, the scientific community, was told, don't put it in. Now, if you look at the 1990, the earlier IPCC reports, and you look at the rate of sea level rise, we're just exceeding the upper end of what their error bars would be. And so what we found over the last 5+ years is that the climate is much more sensitive than we thought 15 years ago. Again, so the IPCC, quite frankly, is a conservative lower limit. Take that as a conservative lower limit, not doomsday. Okay. Now, whether the carbonaceous critters in the ocean lose their carbon shells, whether the conveyor belt of the Gulf Stream goes south and points to Africa, and then England, which is at the same latitude as Calgary, it gets to -30 in Calgary in the winter, Calgary, Canada. It will be a very different place. A lot of the plants in the English gardens will die, to say the least. These things are what I would call low probability, less than 50%, maybe less than 20% in this century. Some of the other things I'm talking about, the increased storms, we see it happening already. The sea level rise, we see it happening, it's at the upper end. The probability that we go up by 6 degrees centigrade if we go to 600 parts per million is about 50%. 6 degrees centigrade, to remind you, is the difference between where we are today and the ice ages, the coldest part of the ice ages, where London was covered in ice. All of Canada down to the United States, Ohio, Pennsylvania was covered in a permanent sheet of ice. 6 degrees colder. So 6 degrees warmer will be a different world. Okay? There's a 50% probability we will get there in this century. So it's prudent risk management at that higher probability that you should put your pedal to the floor and protect it. Is it 95% certain this is going to happen? Absolutely not. We don't really know. So it becomes just insurance. There are other things. There's 90%, the trees, 90% probable. That's going to happen. Okay? Because it's halfway there, and it's happening much faster than we thought. So am I relaxed about it? No, absolutely not. That's why I left a very, dare I say, very comfortable, happy life at Stanford to go to Berkeley. Because Berkeley Lab combination is in a much better position to do something about this. Okay, you can really garnish more resources, and the fact that there's this $500 million national laboratory and a much wider, richer faculty set that you can draw from. And so, no, I think it's really important. I did a major career change. And as my wife knows, there's lots of stuff about this I don't like, but this I believe in very much. And it's so exciting because the students and the professors are enlisting. Okay?
Question at the very back.
Senior I have recently read an article from Dr. Pachauri from IPCC, where he was bluntly asked if he had any prescriptions how to stop CO2 concentration in the atmosphere, and he said the most important, the most critical issue is to put a price on CO2 emissions. That, as far as in this article was concerned, he said it was the most critical issue. Do you agree with that, A? And B, if you agree with that, how is it actually achieved to put a proper price of pollution?
I agree absolutely with that. And in the IAC report, we comment very strongly that that is the way to drive the proper behavior, because you don't make technological choices, you just put a price on the stuff that's going to cause all the things we're worried about, or if not cause it, put us at great risk. It has to be very quickly an international price. If a certain segment of countries do this and others don't, there's economic inequities that will make many people feel very uncomfortable. There are ways of doing this, because that's actually a way to assist developing countries in getting resources over them. It's a price on carbon or credits on avoided carbon. As an economy like India or China grow, that if you avoid, you can take standard building and say if you make it a factor of 3 more efficient, that's avoided carbon. In my mind, that should be as much a credit as decreasing carbon emissions from a coal plant. It should be as much credit as preventing tropical forests from being chopped down. So we absolutely need a price on carbon. It's okay to give industry and countries a 10, 15-year thing. So we're here now, and in 10 or 15 years, we're going to be here. And it's going to be a slow process, no loopholes. Get used to it. This is what California did with many of the regulations and appliance efficiency, installation regulations, and industry. As soon as you gave a signal out here, they got better really fast at the beginning. Right now, they're fighting for loopholes and to decide what price signal. So right now, all the lobbyists and lawyers are employed full-time. In the end, you got to get all parties in each country to decide, no, this is what's going to happen. And as soon as that happens, the lobbyists and lawyers don't have any more leverage, and they sign it to engineers and scientists. This is good, because that solves the problem. And this has played out historically on many, many fronts. And this is ultimately there has to be enough political will to say, forget it. All the special interests who think their business is threatened, and quite frankly, some of them are definitely threatened. But so was tobacco industry. It was threatened once we found out smoking cigarettes was really bad for your health. But in the end, there was enough political will to overcome the tremendous amount of money in the American political system to suppress that. It took a couple of decades. I'm hoping it doesn't take a couple of more decades for this.
It's the gentleman at the back.
I'm Stephen Bishop. I'm also a scientist. But one of the questions I have is about education. I think you're speaking to the converted here. I think one of the problems, perhaps you might agree, is firstly, can we convince the general public? And secondly, can we convince the politicians? So when I drive my car, I only watch the temperature gauge. If that goes up, there's something wrong with the car. I know nothing about cars. Do I need the same in my house? Do I need a CO2 measure in my house to tell me that something's going wrong? And on the other side, how do we as scientists help politicians make decisions? Are we getting it right?
Well, actually, a little meter in your house telling you where you're spending electricity isn't so bad. And many of us geeky technological guys would like, kind of in the kitchen, where it's just the kind of a hub of most houses. In California, we're going to go to real pricing of electricity. That means that hot summer days, you might charge 35, 40 cents a kilowatt hour. And nights, in the winter, you might charge 5 cents a kilowatt hour. Or at nights, in many instances, early in the morning. Electricity, the worth of electricity goes down fivefold maybe even tenfold. It's huge. So you could imagine a meter saying, do you really want to run your dishwasher or your washing machine or dryer when you're being charged 35 cents for electricity per kilowatt hour? You know, why not run it at night? Why is that good? It actually distributes the load. If you look at many sources of energy, nuclear in particular, but also transient sources of energy like wind, which is blowing at night, but nuclear, which it's the capital cost, and you don't want to cycle the reactor up and down. So they're looking for customers to give away the electricity at night. The fuel's nothing. It's 2 or 3%. So there are many, many opportunities to conserve peak loading times. It actually saves a lot of money. It actually drives conservation. My big dream is that you have lots of energy storage things like plug-in hybrids. Suppose 10 years from now we have good batteries and all our cars are plug-in hybrids. So I would program my car, buy electricity at 5 cents a kilowatt hour and sell it back to the grid at 20 cents a kilowatt hour, and maybe I don't go to the market in the afternoon, right? But that's, you know, a geeky technological thing. There's fundamentally all sorts of regulations that we need to make, but financial incentives. So there are opportunities for doing all of this. In the end, though, I think it has to be driven by what I really call risk assessment and what we should do in order to prevent catastrophic things from happening. If half of the things that we're afraid of come half true, it's a disaster. Okay? And that's what we're really afraid of, many of the scientists now who go beyond the IPCC reports and know, oh, you know, there's a lot of other things that have a lower probability of happening, but they're true disasters.
But a local meter would tell people it was right or wrong. I know somebody who does measurements on the ground that is regularly over 600 all the time.
Say that again?
So I know somebody who has got a meter that measures the CO2 concentration.
Oh, the CO2.
At the ground level, it's way over 600.
Oh, yeah, I've got a CO2 meter in my home. It says it's 750 in the house. I'm not really sure how accurate it is. So let me trust the scientists who measure CO2 on this one and say the world average outside, far away from a city, is what it is. I think in a city it's higher. In a home it's definitely higher.
We need to just move on. We've just got time for two more questions, come later, if we may. The gentleman at the front, yeah, and then the lady.
Well, let me go to the second part of the question as to whether we're overrating our impact. This is what you were talking about. This is present time, and this is going back 420,000 years. Red is temperature, black is carbon dioxide, blue is methane. They track each other. These are actually triggered by astronomical events. We don't know what causes this much rise. The astronomical event may cause that much rise, okay? And so, so you think, why are we worried about global warming? Why aren't we worried about global cooling? Because here's where we are today. But we have to dig a little deeper. Right now, that's where we are in CO2, so we're off scale. Okay, and so we think we understand this rise. We have theories about feedback. As the Earth warms up, you release greenhouse gases, and so it's a feedback. The good news is we don't have a Venus atmosphere. Something takes hold, and this is probably slow sequestration. As CO2 rises, as temperature rises, plants take over, and stuff in the ocean takes over. We're fixing that. We're deforesting on a global level. So the ability of the plants to take over has been compromised here, okay? But the point here is that we're kind of on new territory. Now, how new is this territory? Well, if you go back 50 million years, we were much warmer, okay? But the world was a very different place. And so the issue is life going to be wiped out? Absolutely not. If the world becomes 10 degrees warmer, there will be massive species extinction, population displacement, poor people will be wiped out, okay? Rich people are fine. They always can take care of themselves. So it's a different issue, okay? So what was the second?
The commons problem.
The commons problem, big problem. Water pollution is a commons problem that the developed world has figured out. If you're a city, it's always cheaper to dump sewage in the river. It's always cheaper to dump untreated industrial effluent in the river. If you're downstream, it's much more expensive to clean up the water or to deal with the medical issues. So what happened is government stepped in and said, well, for the good of society, it's because the cost is factor 10, factor 100, that you penalize people to dump raw sewage in the river. Now, in the beginning of the Industrial Revolution, for the next 100 years, that's what we did. And then we finally figured it out. The developing countries have not figured it out yet, but we owe it to them and ourselves to try to help them figure out very rapidly that it's much cheaper to treat it at the source. So we did this for water pollution first, then air pollution, in the form of sulfur dioxide, acid rain, all of these other things. We're trying to figure out how to do this with carbon dioxide. Now, is there a hope of doing this? International fishing, there's a little bit of hope. Commons problem, we fish out the oceans, okay? And there's a little bit of hope we can deal with this on a global level, that if we fish out the oceans. Now, you can be pessimistic and say, forget it, live life, enjoy ourselves. But then it becomes a moral issue. What are you really saying to not only your children in this room will be wealthy enough to survive and have a prospect. Not an issue. So it's the average global society that one should start to think about, you know. So I think, yeah, we have to deal with this problem.
So the final question, I'm afraid, from the lady in the third row.
I work for a company, Syngenta, which is an agrochemical company, and obviously we also have produced GM crops as well. And this year there was massive production in the US for bioethanol, of corn being sent to bioethanol, and that's caused some knock-on food security issues in countries like Mexico. And so I'm wondering, how are you advising politicians, because they have put a lot of funding behind bioethanol from corn, but obviously that's not a very good way of using biomass.
It's terrible.
And also affects food security. So what's the current advice that's going into US federal politics to try and
The advice
caution
is that
this?
corn is absolutely the wrong crop. And they're hearing this loud and clear. There's a strong farm lobby that wants to make money. The price of corn in Mexico is a little bit overrated. There's trade issues about corn going from US to Mexico so it's not, you should look into it. It's not at all what you think. But the fundamental question, is corn the right crop for growing biofuels? Absolutely the wrong crop in every respect. It's barely break even in terms of carbon dioxide. It's barely breaking even in terms of fossil fuel invested to fuel gotten back, okay? And you can debate whether it's 20% better, but that's missing the point, right? The cellulose can be a factor of 10 better. Sugarcane's at least a factor of 5 better, okay? So sugarcane's pretty good, okay? But where you can grow sugarcane, Brazil is, and biofuels, you can do it absolutely the wrong way. The worst thing that can happen is that Indonesia chops down its rainforest to grow palm oil. It's worse for the environment, worse for CO2 than if they didn't do anything. Now, Brazil's chopping down its rainforest not to grow sugarcane, Sugarcane doesn't grow in Brazilian rainforests. They're chopping down to grow soybeans. Why? Because China's gotten wealthier. They want animal feed because they want to eat meat. Okay? So what do we do about that? Well, can we tell the Chinese, no, you shouldn't eat meat. People in the Midwest should eat meat. But you shouldn't eat. No, it won't go far. So I think we should educate people that big globs of meat this big are really going to kill you. Or something. Meat is a very inefficient way of using our resources. Right?
So you're saying it's about greater respect for food, in a way.
I think the food, so we actually have a capacity to grow lots of food. If you look, I think even England has a food surplus, but certainly France has a food surplus. Germany has food. The United States has a tremendous food surplus. We took 75 million acres of U.S. agricultural land out of production. We started in 1980 with 420 million acres. We're now down below 360 because of overproduction. We still have overproduction. We still pay farmers not to plant. Okay? So that's why the biofuels, if you plant the right stuff, grasses of some kind, we're talking, and there's part of that, I think 35 million acres is in conservation preserves. You can actually preserve the conservation preserve stuff and just take the current land that we pay farmers not to plant on and some of this other surplus land, and you can have maybe half of U.S. gasoline supplanted, okay? But corn is not the way to do it. We're talking about factor 10 better yield with grasses. It's just a matter of bringing the cost of breaking those grasses into ethanol. That's why BP is willing to invest $500 million. They see a potential, they see a new business. They know that they don't have the technology today, but it's within 5 or 10 years. So to them, it's a business. It's a new wellhead. Okay? But they are smart enough to realize corn is ridiculous. Actually, most of the leaders in the United States actually know this.
So ultimately, corn will be good food.
Corn, you want to, it's very fertilizer intensive. It's very water intensive. We have non-sustainable agricultural practices in the United States. The water tables in the United States are constantly going down, down, down. There's nitrate runoffs from the over-fertilization. So we are actually in a non-sustainable agricultural mode in the United States because of over-fertilization, over-irrigation. These grasses use virtually no fertilizer, or 1/10 of none compared to corn, much less water. So again, it's what you do. But you know, my advice, and it's not just me. I think many people tell the government, and the government actually knows this, that that at best is a transition crop. Ethanol at best is a transition fuel, quite frankly. It's lower. It's too low a density. You actually want to make from cellulose a diesel-like fuel, but diesel engines are much more efficient than gasoline engines. We now know how to make them burn very cleanly. We now know how to trap the particulate matter. They're 30% more efficient. The diesel-like fuels are the things we use in airplanes and trucks and trains. Okay, not gasoline. And once we get plug-in hybrids, we can offload a lot of the personal transportation into another form of energy, but we will need airplane fuel, because I don't see a plug-in hybrid airplane in the near future. Okay.
Well, with that, I have to, I'm afraid, draw the formal proceedings to a close, and like to thank you very much indeed, Dr. Chu. I think you've given us all a much clearer understanding of what we need to worry about. And at the same time, I think you've given us all every reason to wish you a success in your research projects in Berkeley for the sake of us all. And so we're delighted you joined us, and we're delighted Jean was with us too this evening. Thank you very much.